Today we are going to hear about some open problems in Bandit Exploration from Connor Stephens. He's a master student at the RLA lab. Go for it, Connor.
Thanks, Abhishek. And thanks everyone for taking some time out of your afternoon to sit in on this presentation. So first, let's talk about the title, How to Sample When No One's Watching. Now, there's a couple of reasons for this title. One is I think I'm really funny. Don't worry, the illusion wears off pretty quick. The second reason is some of you guys may be familiar with the Bandit framework. And this is usually used as a device to elucidate the trade-offs between exploitation and exploration that we often run into when we're dealing with online learning problems. Now, usually how the Bandit game is played is that an agent encounters a new Bandit instance, a finite set of arms that it needs to establish the best one as quickly as possible. Because every time it samples an arm, it's going to be punished for how bad the arm it sampled was. That is to say, there's quite the incentive for the agent to stop exploring as quickly as possible and begin exploiting as soon as it can reasonably guarantee that it's found a good option. Now we're going to be looking at a slight twist on the framework. I'm going to call it Bandit Exploration. It's also known as pure exploration in the literature, where the agent actually gets free sampling for a finite number of rounds before it's punished solely on its final decision making. So it'll turn out that there's still a little bit of a exploitation-exploration dilemma, but there's not quite the same punishment for exploration, so we're sampling while no one's watching. Okay. This is definitely a problem where the motivation is going to become very important for the main points in this presentation. So what kind of problems are practical when framed as Bandit exploration? And one main takeaway that's especially relevant for a lot of us here is that whenever you're in a simulation-like setting where you're not paying any real consequence for choosing or for taking risks, this is something that you don't really want to model like a standard cumulative regret model. This is more like Bandit exploration. So a couple different examples that I think are relevant for us are things such as hyperparameter selection for your supervised machine learning models. Now, the cost that you're paying here is basically compute time, but at the end of the day, all you want is for the model that you deploy at the end of the day to work well. So this is one of those simulation type deals, very similar to another application a lot of us are familiar with, for instance, Monte Carlo tree search. When we have a rollout policy, for instance, in UCT, some of us have heard of it, we use Bandit algorithms for this case. However, these Bandit algorithms aren't necessarily optimized for just finding the best action at the end of the day. However, there's very related theory, but we don't know that they're optimal for this. Another application that is a little bit further from CS, but is pretty relevant, is let's say you're a company and you're trying to crowdsource feedback for products. For instance, you're interested in what products you should actually continue with larger marketing or maybe just developing in the first place, and you just want to put out these products to people and see how they like them. You're not really paying a large price for showing somebody something that they don't like. They're not really going to boycott your company. At the end of the day, all you care about is finding out what people want. Okay, so it's always helpful if we get into a concrete example, and I have a favorite one that I'm going to be showing to us here. So, of great import, and an actual application of these algorithms has been crowdsourcing the winner of the New Yorker Caption contest. So for those of you who aren't familiar with the contest, how it works is that a cartoon will be put out on an Instagram or otherwise with no caption, and the public will be asked to provide their own captions. And then from there, after the captions have been collected, the public is then asked again to begin to vote on the captions that they find funny. More specifically, how it's been done recently is you can go onto their website and it'll give you a caption, and then you get to rate it as funny, somewhat funny, or unfunny. So for instance, maybe one thing that pops up is A. We see this cartoon here involves two dinosaur lizardy people. There's like a flaming meatball in the background. I'm really not sure what that's about. The first caption says, "One last thing." Okay, so this is kind of funny because it's clear that these guys are going to be interrupted pretty quickly by a catastrophic event. Okay. Option B is, tell me about a time you identified a problem that others didn't see coming. And at around this point, you notice that the lizard person's legs are crossed, and it looks sort of like a business interview or like a job interview. And you're like, This is ridiculous. This is the caption for me. That's really funny. And then C says, I don't know about you, but I can't wait for this day to end. And I'm pretty sure I heard that in the audience today already, so that's clearly not funny to me. But in general, what we want to do is we want the best caption to be identified as the winner. But I'm giving a bit of a subjective ranking here. What we need to do is show these to a lot of people. And if we want to be sure of who the actual winner is, we need to show the thing that comes out to win at the end to a lot of people. So we need a smart way of deciding what captions to show to people so that we can best improve our chances of getting the true winner at the end. Okay, so how can we kind of put this into a framework? So here's one formal definition of this problem. There's a couple different ways you can look at this. This is a fixed budget setting, and I've made it a little more general than you normally see it. But it looked pretty similar to the Bandit framework that people are used to. So what happens is we're going to have a k-armed unstructured Bandit instance. We're going to call it new. For simplicity, all our arms here, let's just say they're univariate normals. We have these means, mu i's, that are in some bounded interval, and we have standard deviation of 1. And now we have an algorithm here. And there's a slight twist again on the Bandit literature, or the standard Bandit literature, in that our algorithm is composed of 2 parts. There's going to be an allocation strategy and a recommendation strategy. And how it boils down to is for 2 rounds. For each round, we're going to sample an action according to our allocation policy, which can depend on the history. We're going to observe a sample from the arm we selected. We're just going to keep grabbing samples sequentially. At the end of the day, we're going to play action A t plus 1. And this action is described, how we choose it is described by some function psi that can depend on the entire history, which looks fancy, but for the most part, usually what we're doing is we're saying what arm had the highest mean after all of our samples, something like that. And then the agent is judged on one number, and this is the loss it receives on its final play. So I'm calling it an expectation of some random loss here. This is for a reason on the next slide. Because, okay, what should this loss be? And the supervised learning people know this is always problem dependent. So for instance, when we're doing this caption contest, in the spirit of a good competition, what we really want to do is make sure the winner gets recognized. So the loss that we are trying to minimize here is the probability that we make a mistake and pick the wrong winner. I'm going to call this setting best arm identification. And so the loss here is just the probability that the mean of the arm we pick is not the best mean. Now, what about a sample that we talked, or an example that we talked about a little bit earlier, such as hyperparameter selection? It's not really a contest. At the end of the day, all you want is a model that performs well. Hopefully, you're able to do this in a sample-efficient way so that you're not spending, $10,000 on compute. And you just want something that minimizes, in our case, let's call it the regret. Or, you've got a best arm identification case. Let's call this good arm identification. It doesn't need to be the best. It just needs to be pretty good. So the way we'll punish this is it's just how much worse your average performance is versus the best you could have possibly done on a given instance. Now, one thing that'll make the discussion a little bit easier to follow is that I'm using 2 conventions that are pretty common from the Bandit literature. One is that the best arm is always going to be arm 1 here, and the worst arm is going to be arm k. The agent can never use this information. You can imagine that some permutation happens in between when these arms are set up. And the second thing is that I'll use the notation capital delta I to refer to how much worse the mean of arm I is compared to arm 1. So for instance, if an arm is equal to the best arm, the gap is 0. If it's a whole 1 unit worse, delta is 1. Okay, so I've described the problem. This is not a brand new problem. What do we know so far? So one thing that should be noted is that best arm identification and the different ways you can look at this has actually received a lot of attention. And we're actually probably in a good place. As of 2016, we had full upper and lower characterizations of how we can reduce this loss in an optimal sense for each instance. We know how well we can do with how many samples. And what it looks like is we can decrease the mistake probability. So in this caption contest, like a negative exponential, where in the numerator we have capital T, which is a reminder is the number of samples that we have access to. And in the denominator, we have 2 factors. I'm not going to worry too much about the log k, but this is the logarithm of the number of arms we have. And then there's an H factor here, which is a complexity measure for finding the best arm. And what H looks like is it's almost a measure of how similar the rest of the arms are to the arm you're trying to identify. It's a sum over these squares of the gaps between arms. So for just better intuition, if you had an arm that was extremely similar to the best arm, it would be very difficult to distinguish these two. And if you think about what this does to this summation, it would contribute a very large term to your summation. So this is sort of like a measure of how similar the arms are. And this makes a lot of sense. And we have algorithms that actually achieve this bound. So what's the problem? Well, the problem is that a lot of algorithms out there have been designed for best arm identification to optimize this loss function. And they're being applied to settings where realistically what we care about is regret. So is this a problem? Well, that's a decent question. Let's get back to cartoon captions, because you guys didn't have enough of that. Okay, so we're back to the cartoon captions, but now we have the additional ground truth TM machine. And it tells us the actual funny of each caption. So for instance, B, we all knew was the funniest. It's actually a funny of 1. And the other options are funny of 0.4 and 0.3. And we imagine that we're Bob Mankoff and we're trying to identify the best arm with high probability. And we fix the number of samples, we run our algorithm. How well do we do? Actually, what if we change ground truth though? Let's say we do the exact same thing. We have the same number of samples. We have a new ground truth though, ground truth 2.0. Now what's happened is that in this alternate universe, caption C is actually pretty funny. It's almost as funny as option B. So what happens? Well, in best arm identification, which is what we were interested in, we've tanked our ability to distinguish these two best arms. I tried to put a frowny face, but that's not a template on Google Slides. So there is an upside down happy face and it's red. So I think you get the idea. But this complexity measure that we care about for actually getting the best arm has actually gone up by a factor of like 20. However, let's say I'm Bob Mankoff again, and all I want to do is show people a good caption cartoon combination. Well, then the situation looks kind of different. While it's harder for me to actually identify the correct winner of this contest, if we consider a really poor strategy that randomly selected one of the captions uniformly and how badly it would do, on this second instance, the regret of this instance is halved. It's way easier. So it's harder to get the correct arm. It's easier to do well, whatever this means on this instance. Now, I don't know, this isn't necessarily too deep. These are obvious conclusions, but maybe it's a head scratcher that it's not quite as simple to just use these algorithms on a loss that you haven't optimized for. So this raises some concerns. Now, the first concern is that we have algorithms based on best arm identification. We have good theory for this. We have sample size guarantees that let you basically make a certificate that says after this many samples, I can guarantee you that your confidence is this. But in lots of practical situations, it just doesn't mean anything. So for instance, let's say you have a ton of arms, you're Bob Mankoff. I'm Bob Mankoff a lot, as you can tell, but there's thousands of captions. There's very little chance that your probability of actually identifying the best caption approaches anything like 0. So instead, what you're getting is results that say like, well, I can improve your mistake probability from 0.7 to 0.5. And you say, is that good? Like, there is an improvement. However, there's no guarantee that something else kind of screwed up doesn't happen. For instance, there's no guarantee that your regret becomes better controlled. That is to say, that does tell you that you put more mass on choosing the best arm. However, maybe rather than being a monotonic increase in probability from the worst arm to best arm of choosing it, maybe instead you switched it to a coin toss where you either choose the best arm or the worst arm. This is kind of garbage behavior, but it still fits within having improved your probability from 0.7 to 0.5. Okay, so maybe we don't always want to care about just the probability. So maybe the regret loss is a more practical measure of performance in many of the applications that we actually deal with. Now that's kind of a concern if your algorithms are designed for best arm identification, where it's possible that this objective forces you to do sampling that's a little bit too conservative. If you want the best arm, you can leave no stone unturned. simple, or calculating the regret necessarily is a little bit more lenient in this aspect. If you choose a nearly suboptimal arm, you don't pay a heavy cost for this. Now, there's no smoking gun that these are different objectives in terms of one allocation strategy yet. So let's get a bit more concrete about the open problems that we're looking at here. So let's simplify things and only care about the allocation strategy that you're doing. Because let's say our recommendation strategy is something nice and simplistic and common sense, like we just choose the arm with the highest empirical mean after T rounds. So one important question is an allocation strategy that is good, and by good, I mean instance optimal, for best arm identification, also going to be good at this regret loss? Can we transfer algorithms from one loss to the other? That is, if you want to get philosophical with this, is looking for the best arm sufficient to actually find a good arm quickly? And it sounds, ridiculous that you're saying maybe optimizing one loss with an algorithm designed for the other one doesn't work, but it's not entirely clear. Now, a second question is, regardless of what the answer to the above is, it would be important to know how the instance optimal scales as T increases. That is to say, if we're going to design to easy instances, give you great sample complexity, well, we need a theory that tells you what are the limits on what you can do. Given a certain problem instance, how many samples do you need? Are the algorithms that we have already achieving this? Now, to that extent, there's some ongoing work that is in pretty early stages. So it's happening with Csaba Sepesvári and a collaborator from the University of Arizona, Kwang-Sun Jin. And so the kind of questions that we're interested in asking and looking at are things such as, are there adversarial examples? Probably better describe them as environments where you can tune the environment such that an allocation that is doing this very careful sampling to ensure best arm identification will fail to reasonably optimize the regret loss. That is to say, is there another allocation that you could have used that will much more quickly give you a low regret because it's not constrained to be so conservative? Now, a second thing, like I mentioned, is we need to understand these fundamental limits on how well you can do on the regret loss, regardless of whether it's the same. Many times, you do just care about the regret loss. So we're trying to understand what is the lower bound here. And one approach is to consider the performance of what is basically an allocation oracle, where if I actually tell you complete information about the Bandit instance, so I know the identities of the arms in terms of their means and their indices, and then I just perform non-sequential allocation. So I say this arm gets this many, etc. What is the limit on how well you can do if at the end of the day, you have to recommend an arm based on empirical best mean? And then finally, in terms of actually looking at some new algorithms that might be better suited for this regret loss than in terms of something like best arm identification, there's been some recent work by another group, Samuels and Jameson, which has provided some quite interesting suggestions for how you can be more aggressive in adapting to easy problems, which is a lot of what the suspicion is here. That while these algorithms aren't bad for simple regret, maybe we could be doing a lot better if we weren't so hamstrung. So one of their main ideas is that we can do some random subsampling of arms. And this isn't necessarily a brand new idea in online learning. For instance, many algorithms for best arm identification involve rounds of elimination of bad arms. But the idea here is that right from the get-go, if you subsample the number of arms that you care about and are sampling, if your instance is easy and there are many good arms, well, so long as one of those good arms ended up in your initial subset, you should be fine for your regret at the end of the day. And because you're considering a smaller subset of arms, you're able to dedicate more resources per arm to better highlight the difference between this good arm and the rest. So this is basically an idea where you're going to need to, in a clever way, decide on the size of your subsamples, but this gives you a way to tune the performance of your algorithm to take advantage of easy instances when they exist, but still eventually recover to at least reach minimax performance when your instance is hard at the end. Now, this is all I have for the slides for this presentation. I would like this to be, hopefully we can have a good discussion on this. One thing that I'd love to hear about from people are, for example, do people have ideas on where you would expect to see examples where looking for the best arm is at odds with finding a small regret loss? Are there obvious situations in terms of how your arm should be separated? Is it the region of just many, many arms? Is there a sample? Well, we know it shouldn't be asymptotic sample complexity, but these are things that we're interested in still working on. And a second, maybe more philosophical topic that I think fits with this is that in many cases, the measure that we are trying to optimize may not be realistic for us to get good performance in our sample regimes. For instance, in the cartoon example, we're not going to find the best caption. So in these cases, is it more appropriate to just cut our losses, pun unintended, and switch to a different, more reasonable measure? At what point do we choose to just throw away an idealistic loss and go for something that is more practical and realizable? Thank you very much.
Well, I guess no one else is saying anything. I think you posed the question, what settings do people have maybe where best arm identification wouldn't be the right thing to do and maybe you want to do something different? I don't really have an answer to that question, but I can tell you about a setting where for us best arm identification wasn't interesting or wasn't what we wanted. But it's possible someone else has a more pertinent question, a pertinent thing related to your talk.
Yeah, I think more what I was getting towards is, for instance, we can create, there's relatively obvious examples where given the sample regime that you're in, there's no way to get what anybody would call a good loss in the mistake probability regime. That doesn't mean that it's not a good thing to look at. It's still something you can improve consistently. It'll just improve very slowly. I guess more so the question is there an example where these two objectives are at odds in the optimal sampling? And of course, this is an open question for a reason. If somebody is able to pipe up and go, ah, yes, it's this one, I would be kind of disappointed but happy at the same time.
Does this setting assume Gaussian rewards? Because I would imagine if you had very fat tail rewards and then your statistic was not robust, then it could throw things off, maybe?
Yeah, so I've specified Gaussian rewards in this case, but in general, the literature is focused on namely sub-Gaussian, just anything that concentrates fast enough. Fat-tailed isn't really the kind of phenomenon that I guess I'm discussing for being a confounding factor, but I appreciate what you're saying. Yeah, if you don't have the exponential concentration, then it's a lot harder.
I think Chad was going to say something. Maybe I want to understand more exactly the difference between the regret loss and the best arm identification. It was an expectation over XAT, and now maybe I'm realizing I don't understand that well enough. Could you?
Sure, sorry. So it's basically in Bandits, there's the usual expected regret. And this is essentially the cumulative regret from Bandits, where you only care about the regret you incur in the last round. So more specifically, I sample a Bandit instance for T rounds. I decide the arm to pull afterwards based on it having the empirically largest mean. And then I look at the expectation of if I follow that allocation strategy and that recommendation strategy, basically how good is the action that I would have taken. And the regret is defined as the difference between that and how good I could have possibly done. So
Gotcha.
the main...
So then,
sorry.
Is the expectation then, what I'm trying to see is what's random here. So is the expectation over the T things you could have seen in the first T rounds, assuming that you're following this like fixed pi in U, or is there some randomness?
Yeah, so the expectation here is over the randomness in the instance over the first T samples, which can also be some randomness, and there's also some randomness allowed in your algorithm. So basically, yeah.
So just a clarification question here. So you could replace the X with some U here, right?
Yeah. It's
interesting. Yeah.
Right, because the A is the random thing, I guess, not the mu.
That's the main source of random.
Sorry, yeah, X was mentioned once, so maybe it was a little confusing to drop it just in the middle there.
Right. So Connor, did you run some experiments? No.
I did run some experiments. There's a message waiting for you on the Slack channel. It's less hopeful than we'd hoped for, but
Okay.
yes, the hunt for the smoking gun resumes.
What was the experiment?
It's along the lines of we're still looking at these allocation oracles. It makes the problem of you don't actually have to create an algorithm which is designed for minimizing simple regret as opposed to best arm identification. You can simply run experiments like I'm discussing in this slide here, where you fix the allocation for each arms, or sorry, for a set of, say, good arms and bad arms. Let's say you identify the ratio of pulls that you identify to the good arms versus the bad arms, and you adjust this ratio to basically discover what should an algorithm do if you want to optimize, say, best arm identification versus this simple, this regret loss we have here. And so the curiosity is there a allocation ratio that does well on one that doesn't do well on the others? Although at the moment, what we're dealing with is there is a hunch that a really important thing for minimizing regret is this idea of subsampling. Because in most of the algorithms that are in place right now, let's say there's two good arms in the instance. Well, if they both look as good as the other one, most reasonable algorithms are going to sample each arm equally. So in a way, they're almost cannibalizing samples from each other, versus if an algorithm is able to only select one of those good arms and dedicate all of its resources to sampling that one good arm, you would be able to better differentiate that one arm from the rest of the instances. So we're thinking that the Oracle models that we're looking at right now aren't able to fully capture the benefits that this subsampling would let you, or this subsampling can provide to you. So we're working on that.
So it's somehow somewhat surprising to me that this is such an open problem that mostly has been focused on best arm identification. So you're saying there's not really a lot of algorithms or any algorithms that look at minimizing the regret loss?
Yeah, so more or less the history of things are in, Chaba can correct me if I'm wrong, in a 2010 paper. At first, they looked at epsilon delta pack results for this setting. So you can reach an epsilon good arm with 1 minus delta confidence, and they did that in around 2004. And in 2010, a group was looking at simple regrets. And within a page and a half of the paper, they say, well, simple regret is related to the mistake probability on your instance. There's a bound that exists between the two. And therefore, if you do well on the mistake probability, reasonably you do well on simple regret. And then it just kind of went from there. There is some analysis of the simple regret of algorithms that does exist. The gaps are mostly on what is optimal in these instances. And as far as these kind of results, this has all not happened yet in comparison to best arm identification. And a lot of that relates to the fact that it is just straight up more difficult to analyze optimality in simple regret versus in mistake probability, because the complexity of the losses respectively, the mistake probability is only one probability term, but your expected regret is a summation over the suboptimality of each arm and the probability of picking each arm. There's in no way does it get easier. So because of that, best arm identification has seen a lot more work. And to be clear, I don't think that's bad. There's settings where it's a completely reasonable strategy, and these algorithms don't seem to be bad for simple regret. It's just maybe it's time that we try and get some results in the setting.
Yeah.
That just seems like a reasonable thing to say. I mean, I guess the analogy to RL is maybe we suffer from the same problem. We're always trying to identify the optimal policy instead of looking at regret more. But I guess lots of people do look at regret for the policy as well. So maybe it's not the same problem.
It's like in RL, if you would say that I only care about if I find the optimal policy.
Mm-hmm.
Like, but no one says that because there are so many policies, even if you're just considering, finite MDPs, and you have exponentially many policies, so you know that you would never find it if you have simulation data. The probabilities are minuscule, so you don't. Yeah, like we don't usually analyze RL in terms of probability of missing the optimal policy.
Right.
Also, we know that the gaps between an optimal policy and the second best policy can be so small that we would not care at all.
Yeah. I feel like it would also be bad of me to not point out the fact that just because I've talked about best arm identification and simple regret, people have recognized the gaps in the literature. So there's actually been many branches in ways to understand this pure exploration. Like I talked about epsilon delta pack. There's this whole top K arms situation where instead of just caring about the best arm, you care about the top K arms. How well can you do? There's lots of work on thresholding bandits where you just care about finding arms above a given mean. It's definitely been recognized that many of these applications, you care about different things, and it's kind of splintered off in many different directions where they're clearly related. Simple regret is just a lot conceptually easier, but more difficult analytically.
Can I ask, which one is Thompson sampling doing?
When you say which is it doing, which is it optimized, I think there's optimality results for Thompson sampling in cumulative regret, but I don't know whether there's optimality results for best arm identification. Maybe Chaba would know, but it's designed for cumulative regret minimization, which it turns out is actually pretty good for pure exploration as well. It's just that it's unclear in what sample regimes is this the best and how this relates to being optimal in simple regret. So long story short, it's for the cumulative regret setting.
Connor, can we go over the example again where you showed that why we should care about the regret loss?
Well, so why we should care about the regret loss? I guess the most succinct way of putting it is kind of cynical. One reason why you should care about the regret loss is in most realistic situations, you're never going to get a good number in your best arm identification loss. So why not try something that you actually have a chance of getting small numbers on, or numbers that you can understand. Actually, this is probably what you're talking about. One reason why best arm identification can have some kind of unfortunate effects is what I'm discussing in this bullet point here, where, for instance, frankly it's a little disingenuous because most of the algorithms that actually do best arm identification, it would seem very unlikely that this happens. But in theory, if you're trying to optimize mistake probability, it's possible that after you take more samples, your mistake probability goes from 0.7 to 0.5. So you have more samples, you can guarantee this improvement with high probability. But there's no, that doesn't necessarily mean that the distribution of the returns, the regret on your algorithm at the end of the day is well controlled. So the example that I gave is, if you imagine, I guess, let's say you have 3 arms, and my arm is going to be the probability mass for choosing each arm at the end of the day. And when the peak here, there we go, got it, is 0.7. And then let's say you improve your probability to 0.5. So you increase the probability of choosing this best arm. So this part goes up. But then you tank the middle, and all your mass is split between the best arm and the worst arm. Still so that you put more mass on the best arm, but now the rest of the mass is all on the worst arm. So you still have more likelihood of picking the best arm. However, now you're in a situation where your algorithm is either returning the very best answer or the very worst answer. This is not like a better shaped distribution, like it's like high variance, it's very unintuitive, and most people wouldn't say that's performing well, but this is still, you know, that's fits within having reduced your mistake probability. And the second instance is simply that there's lots of applications here where you don't really care about choosing the best arm. Like I gave the example of hyperparameter optimization. Nobody has ever asked, do you have the best parameters? They just say, does this actually work? Does this achieve 0.001% more on the benchmark? They just want to know that it's good. And this is more true to the regret.
Great, thanks.
Would we ever want to mix these? Like I imagine like in medicine, you might want to avoid the worst case, but you also might want to try to get the best average case. Like, is there some kind of continuum between these good arm and best arm? And maybe avoiding the bad arms? That was another question. Is avoiding the bad arms kind of the same as?
Yeah, I think maybe Chuba has something he wants to say here, but one thing that you can extend, like in the regular bandit literature with cumulative regret, one thing that's important for some algorithms is controlling the regret with high probability. So not just an expectation. So for instance, if anyone recalls the Bandits course, and that's not bringing up too many bad memories, there's examples of algorithms that work well in expectation, but they have the unfortunate feature that with reasonable probability, they give some absolutely garbage results. And to improve upon that, you need to create algorithms which have a well-controlled regret within high probability. And this sounds like sort of what you're discussing here, where like it's unreasonable to find the best arm with high probability, but at the same time, you still need to care about more than just the average case in medicine. So I think that maybe the most analogous objective there is controlling the regrets on the last round with high probability. And that's actually pretty similar to what the group, this Jameson paper is discussing, is it's very similar to a high probability bound on the simple regret.
Maybe I'll ask one more question. So, as I understand the Bandit algorithm, they work by learning the Q values, and then you choose the action based on some algorithm like epsilon greedy or say UCB, right? So, is it would that change when you're solving for the regret loss?
So maybe just when we're actually talking about, I guess, normal Bandit algorithms, maybe talking about regret loss starts to get a little bit confusing. Let's talk about last round regret versus cumulative regret. So the algorithms that you're discussing are usually caring about cumulative regrets. So this is when you pay a penalty for every single sample that you take. So yeah, the epsilon greedy is a thing. UCB, these are all strategies that apply for this. And if you're asking, are these strategies applicable for this last round regret? Like the simple answer is yes, they seem to do reasonably. The intuition is that if you're not being punished for sampling in every single round, reasonably you can get away with a little bit more exploration. And you shouldn't necessarily use the same exploration bonus here, like in UCB. Whether or not, how much better you can do than a cumulative regret optimizing algorithm is one of the open questions in how well you can do for simple regret, or for last round regret, sorry. And to be, I guess, further explain, empirically what seems to happen is that one of these algorithms, they will do quite well in the regime where you have fewer samples. Because they're designed to optimize cumulative regret, they very aggressively go after the best arms that they can. And this tends to result in them choosing a good arm initially. However, as you get into the regime where you can sample arms for as long as you want, algorithms that are more explicitly exploring all options take over in the regime where you just have lots of samples, just because they won't miss an option that a cumulative regrets algorithm may have avoided because it didn't look initially good.
Yeah, thanks.
Hey, Connor. Thanks for the great talk. I guess I had a question, but let me preface it with saying I know very little about bandits. I agree sort of a little bit with your philosophical point. At least to me, it's not immediately obvious that minimizing the probability of choosing the wrong arm versus choosing just a good arm, like they would inherently have the same strategy. I guess in particular, in Bandits, do you care about like the scenario where perhaps there's more arms than even number of pulls that you get to do? Because that's a scenario that I would have imagined sort of those two would diverge.
Yeah, you'd imagine, right? I mean, in the probability case, the answer is sort of you're screwed to a certain extent. So I think we're agreeing with you in the sense that, like, saying that you have more arms than you have samples, I think we're leaning more towards just that you have a moderate number of samples, not a whole ton. I'm trying to think of what you can say when you have fewer samples than you have arms.
Like, so again, I'm a little bit worried about sort of going out of my domain of knowledge, but like if you have, let's say, 100 arms and 90 samples, I imagine best arm, let's say 80, like you've done 80 of your samples, they've all been, or 89 so far, all been trash except for 2. And those 2 have been very high. It's like if you want to minimize the choice of doing the wrong one currently, so you can either choose the unknown one or one of the 2 good ones. I was just curious if this is an area that you guys even care about, or.
So there is a related topic. This gets sort of into infinite armed bandits, which is basically what you're talking about, where you can't possibly sample all of the arms, and there what actually happens is there's like a warehouse of arms that you haven't seen yet that you could bring into the mix and then start sampling, and maybe there's some structure as to what the arms coming out of the warehouse will look like, but it's the regime where you need to decide whether you stick with the arms that you've already checked out or whether you're going to pull a complete unknown arm out of the warehouse. So this sounds a lot like what you're talking about. I'm personally not very familiar with the literature, so I can't speak too much on the results, but I would be happy to direct you to some of those papers.
By the way, so isn't this related to the research direction that we started on, right? Like if you add some more structure, let's say the reward function is going to be concave, right? Yeah. Do you want to say a few words for that?
You just mean about the online convex optimization sort of side of things?
Yes.
Yeah. So like how I started caring about this was initially coming from a sort of different perspective, which is similar results in the online convex optimization literature. Basically, are there instance-dependent lower bounds about stochastic convex optimization. And this is a case where there is more structure, but actually one of the struggles when I was working on this is that there was no analogous regret analysis for bandits, which would have been very nice to at least try and draw some tools. Now, ironically, there's almost like the intersection of results between one field and the next is like 0. So in the online convex optimization case, most of the analysis for algorithms is all about, you can say that the expected suboptimality of your final iterate is this for some function of t, like that's the standard result. This is what we're looking for in bandits, versus the like a good iterate with high probability, which is something that we do have in bandits, is something that's missing in the convex optimization literature. So one nice thing for me certainly is that if we make some progress on the bandit last round regret, this would lead to some pretty interesting results in the online convex optimization literature, where you can start to do more work with what are the lower bounds for how algorithms can adapt to an online convex optimization problem.
So maybe just a comment about cumulative regret minimization and last round regret minimization. So if you take the, like Connor tried to explain this, so I just want to add a little bit more to that. If you think about what those algorithms need to do, they have to be careful not to pull too bad arms. Versus if you care about the last round regret, then all these considerations about being careful are out of the window. You can be as reckless as you wish, as long as in the last round you find a good arm. And indeed, that's a big difference between the algorithms. The way they are controlling the information that they are collecting is rather different. So what happens in the cumulative regret minimization algorithms is that they are gonna pull the optimal arm just barely enough to know that it's optimal. Like they try not doing that too much, and they pull the suboptimal arms just barely enough to know that they are suboptimal. So rather than them being very confident about the suboptimal arms, they're really unconfident about the suboptimal arms, which is okay if you care about cumulative regret, but it's not necessarily so great if you care about, let's say, best time identification. So definitely in best time identification, this is not a good strategy. So the cumulative regret minimization algorithms, the probability that they're not going to find the best arm usually decays polynomially with the number of rounds. Like they're really miserable algorithms, because even if you just use uniform allocation, then the probability of misidentifying the best arm would decay exponentially fast, as was shown on the slides too. Yeah. So that kind of answers like whether Thomson sampling is going to be a great algorithm. Well, in best time identification, it's not. We don't quite understand these relations yet in simple regret, but maybe this also suggests that it's not going to be that great in simple regret either.
Maybe just to jump on, there's with everything that you were saying just now, there's a lot of caveats that you need to attach about the sample size regime that you're in, because like when you have a ton of samples, some really dumb algorithms work. When you have very few samples, there's like nothing you can do that will do well. So it's very tricky to work out what is a reasonable number of samples to be considering when you answer questions like, is this algorithm good or not?
Yeah. So in particular, my comment was about the large sample regime. Like in the long run, these algorithms are not super clever. But you may not care. So that's the other thing, that like when the polynomial mistake probability is so minuscule that I mean, yeah, the exponentially small probability is even smaller, but maybe you don't care about those differences. So it's kind of tricky. The interim regime is what is the interesting, but that's the regime which is really hard to understand analytically. Yeah. So wish good luck to Connor.
All right, if there are no more questions, let's all thank Connor for an interesting talk.